Welcome everybody to this plenary talk by Professor Yi Huang. A brief biography. Professor Yi Huang received a BSc in physics from Wuhan, China, and MSc in microwave engineering from Nanjing, China, and a PhD in communications from the University of Oxford, United Kingdom. He's interested in the areas of antennas, radio propagation, radar, wireless communications, energy harvesting, and applied electromagnetics. His experience includes 3 years with Nanjing Research Institute of Electronic Technology in China as a radar engineer, and various periods with the universities of Birmingham, Oxford, and Essex as a member of the research staff. He worked as a research fellow at British Telecom Labs and then joined the Department of Electrical Engineering and Electronics at the University of Liverpool, where he is head of the High Frequency Engineering Research Group. The title of his talk is Wireless Energy Harvesting and Wireless Power Transfer from RF to Optical Frequencies. Let's welcome Professor Yi Huang.
Thank you for this very nice introduction. Welcome to this seminar, this talk. And I'm from Liverpool University in the UK. And here is a picture of some of my group members. As you can see, we are very international. Okay, and before I discuss wireless energy harvesting and power transfer, probably I would like to introduce you to Liverpool first. Yeah, I guess most of you heard of Liverpool, but not necessarily know where Liverpool is. Here's the map of the UK. London is in the south, as you can see, yeah? And the Liverpool actually is right in the middle of the UK map. Okay, so we have a bigger brother next to us. It's called Manchester. Okay, Liverpool, Manchester, we are very close. Okay, we also compete against each other. Okay, Liverpool City has got about 500,000 people. Okay, if you consider large area, then we have about 1 million. Okay, and Liverpool is famous for a number of things. Probably the first to some people is the music. Okay, the Beatles in the 60s, and then they were the world #1 for a long time, and of course football. Okay, I know Brazil is also very good at Mexico, Brazil, and South American countries all good at footballs, but Liverpool is also very good at football. We were the champion of the Champions League last year. Okay, the university is one of the Russell Group universities. Okay, so it's equivalent to the Americans Ivy League. Okay, and we are associated with 9 Nobel Prize winners. Okay, we have about 7,000 staff. Okay, so we always ranked in world top 200, typically 100, probably 30. Okay, so that's about the city, the university. Let's focus on our technical side. Okay, first I will give you a brief introduction, and then we will discuss wireless energy harvesting and then wireless power transfer. I will finish my talk with some discussions and draw conclusions. Okay. Right. As you may have noticed, I use wireless energy harvesting, but not wireless power harvesting. And then I use wireless power transfer. So here we have two nouns, energy and power. So these two are closely linked. but many people are confused by these two basic concepts. So I think we need to clarify that. Okay, so what is the main difference between energy and the power? So the definition of energy is the capacity to do work. Okay, and then the power is the rate at which the work is done. So therefore, energy is the integration of the power over time. So for example, here there is a bulb. Yeah, we typically say, oh, this bulb is say 60 watts. Okay, 60 watts is what? It is the power. Okay, the power consumption over 1 hour, then that is how much energy the light bulb has used. Okay, so that's the linkage between energy and the power. So in terms of the source of the power we use, and the major source, actually the largest one is what? Is the solar energy. Okay, the solar energy is really the energy source for all the powers we have used. Okay, and then this figure basically shows the power density. Okay, power density as a function of frequency. Okay, and as you can see, the visible light area, has got the highest power density. Okay, and that's why we have solar panels. Solar panels basically to collect the energy from the sun. In that region. Okay, the formation of a solar panel basically, start from cell, modules, and then array. Okay, in terms of the theory, then it's what? In terms of the theory, then it's the band gap effects. Okay, so we need to have N-type, P-type, then we have a kind of PN junction. Okay, so therefore, we use band gap effects to generate, to harvest energy from the sun. But unfortunately, the energy conversion efficiency for a single junction, say silicon-based PV, okay, photovoltaic solar cell, the maximum power conversion efficiency is about 30%. In reality, okay, so here is a plot of the best, okay, cell efficiency as a function of time, and now it's 2025. Okay, so as you can see, the single junction conversion efficiency here actually only about 20%. Okay, so the best one, multi-junction one, actually, is less than 50%. So there is a kind of course, the trend is getting better all the time. But there is a fundamental limit, for this kind of technology. So we would like to see if there is a better way to convert, the solar energy to, for us to use. So even 1% improvement, that would be significant. So that's the major motivation for us to study energy harvesting systems. So in addition to solar energy, we do have energies from other sources. For example, radio microwave sources, from radio base station, for example, Wi-Fi. And then, so that basically can also be classified with the background ambient electromagnetic radiation. Okay, can be intentional or unintentional. Okay, there are other forms from such as vibration, motion, thermal effects, so on and so forth. Okay, so if you look at the power against the applications, so here is a very nice plot from a reference. Okay, and standby mode, typically power consumption is very minimal. Say in the 10 nanowatts range. But if we talk about the most popular device we use, which is it's a mobile phone. for the cell phone, and then the power consumption typically, yeah, it's about 1 watt or even less. Okay. So for a lot of devices, small devices, especially in the IoT era, okay, the power consumption actually is less than 1 watt. Okay, for example, watch, yeah, calculators, and that power consumption is just 1, yeah, microwatt. So that is a kind of small power, but it doesn't matter how small, how big, we need source. At the moment, the source is for most of such devices, it's either powered by batteries or cables. Yeah, so both batteries, cables are not good. Yeah, batteries not environmentally friendly. It runs out every yeah, depends on the device. For example, the clock in my office, I have to change the battery every 6 months, for example, which is a bit awkward. Yeah, and then some device powered by cables, that is also awkward, basically not movable. But the solar energy then would be good. Unfortunately, yeah, it's not available everywhere. Say in my office, then I cannot harvest solar energy. So people would like to get, yeah, things powered by wireless way. Okay. Actually, in the very early days, Nikola Tesla, now we all know, yeah, this name by Elon Musk, Tesla car. Okay. But himself actually is a great inventor, invented a lot of things. Yeah, he also had a kind of battle, yeah, well, against some other, yeah, great guys. But as you can see from this figure here, one of his early work, actually the largest project he has undertaken, is this wireless power transfer system. Because at his time already, yeah, electricity is available through cables. Then he thought, okay, why not if we could power, the light bulb using without cable, then that would be great. Okay, so as you can see from this hand drawing here, then that's his transmitter and the receiver. Yeah, basically he has got this L and C, that is a resonating circuit. Yeah, not very far away, and then there is another, yeah, L and C, and this L then basically nowadays we call a Tesla coil. Okay, so he was the first person to do it, but unfortunately, he didn't make it work. I think the main reason was the rectifier at the time was not very good. Yeah, so the power actually could not be converted to say DC. So after many years, around the 1960s, okay, so a group in the US led by William Brown, and they managed to implement, yeah, the Tesla's idea, but I realized that a microwave frequency manages to, yeah, transmit energy wirelessly, and so that was a success. More recently, yeah, as many of you may have seen this picture, yeah, this is a group from MIT. Okay, so they managed to use some resonating, yeah, circuit, and managed to transmit wireless power over 2 meters or so. Yeah, and then as you can see, the light be as well by the side. Yeah, is on. That's basically turned on by, yeah, wireless power. Okay, so that means, the idea basically initiated by Tesla works. Okay, the idea actually is something nowadays we call it rectangle. So it's a combination of two words, rectify and antenna, or say rectifying antenna. As you can see from this, yeah, diagram, signals, yeah, is received by antenna through a impedance matching network, and then rectifier, yeah, so the output then can be used, yeah, for a device or to store it in the battery. So RF power then converted to DC power. So that's the basic function of a rectangle. Why we're interested in this? Yeah, the main reason is the possible high energy conversion efficiency. So here is an example, okay, demonstrated by Xu and Chen, okay, both were in the US, okay. That demonstrations system is relatively simple, as you can see. Yeah, the left-hand side basically is a transmitter, okay. The right-hand side then is a receiver, and this receiver, the main element is a rectangle. So the antenna rectifier highly integrated. So let's have a look at the result, okay? And the energy conversion efficiency, as you can see, is not 30%, not 50%, but it can be more than 80%. So that is very attractive compared with our solar panel approach. And then, of course, one thing you may notice here is the energy conversion efficiency is a function of the load resistance. So it's not a constant. So this is we call a nonlinear effects. Okay, so that probably is an issue. I will discuss that further. So the idea is very attractive. So we actually worked on this, and then we developed a design, as you can see here. Okay, all these dimensions actually it's in nanometer. Okay, in 2009 at that time, nanotechnology already available to us. We actually fabricate this design and then try to harvest some solar energy, actually far infrared, not the optical band. But unfortunately, it didn't work. Okay, and the idea, in theory, it should work, but in practice, it didn't work. Okay, the main problem actually was the rectifier. You know, the diodes at this kind of a high frequency, it doesn't work. In the not just us, and all these labs, as you can see from Colorado University, Rice University, and the other labs, they all designed something, made something, but nobody has made it work. So that's a disappointment result. Yeah, but we like the idea, the rectify. So therefore, we shift our frequency down to RF microwave. So that is why in the title, I said from low to optical frequencies. Right, so low frequencies, RF microwave. So we have signals from such as television broadcasting tower, radio tower, mobile cell stations, Wi-Fi, so on and so forth. They transmit electromagnetic energy at relatively low frequencies. So if we use rectangle to harvest this energy, and then here are the major features, okay, in green, okay, low power density, for example, possibly wide frequency band. If we use rectangles for wireless power transfer, and then the features, is different, such as the experiment conducted by Tesla. It's typically fixed frequency, narrow band, and possibly high power. So the common thing is about rectangle. Okay, and if you search the most popular database, say IEEE Explore, you say what is power transfer, and then you can find probably more than 35,000 papers there. Okay, and interesting enough, you know, this I think most of you cannot read it, but what this means actually is that every year the most popular papers in IEEE transactions on TAP, transactions on antenna propagation. Okay, so as you can see, this 2015, we actually have this rectangle. Okay, so this is in Chinese means rectangle. Okay, and then 2016, another popular antenna, paper is on rectangle as well. So yeah, but both were from our lab, as you can see. Yeah, here is my name. So that basically shows the trend. You know, of course now, say in nowadays, okay, rectangle is no longer the most popular area, but it was extremely popular around 10 years ago. But still, yeah, rectangular technology is attractive. So more recently, there was a special issue on the proceeding of IEEE. Okay, so as you can see in this special issue, okay, it had I think 10, yeah, invited papers. We were among these invited papers. We contribute one in metamaterials and the meta surfaces for wireless power transfer and energy harvesting. Okay, so if you are interested in this topic, so this special issue is highly recommended. It's given by some top researchers in this area. It has got extremely good coverage. Okay, so that's my introduction. Okay, now you know why I did work in this area. Now let's focus on wireless energy harvesting. As I mentioned, so for wireless energy harvesting, the main device we need is rectangle, which can convert RF microwave energy to DC energy, and so for this purpose, harvest energy, we would like the rectangle to be broadband, because we would like to cover the source as widely as possible, the source from TV, from mobile, from Wi-Fi, or from other unknown one. Narrowband, then you limit your the source available to you. So there are many challenges, and also you need to take a lot of practical things into account for wireless energy harvesting. The first one, as I mentioned, is the bandwidth and also efficiency. We would like the efficiency bandwidth as large as possible. So that's number one. Number two, because signals are coming as electromagnetic wave. Electromagnetic wave basically has got polarization. So you would like your rectangle, your antenna, to be dual polarized or circular polarized. So therefore, it doesn't matter which orientation of the wave your antenna will pick it up. And the third thing is it's radiation pattern. You don't know where the wave is coming from, so you would like the beam to be relatively broad. So we say broad beam width. So therefore, signals can be collected. And there are other considerations, such as the size. You would like it to be as small as possible. The cost as little as possible. As a practical product, then you need to take all these kind of things into account. Right. Let's deal with these challenges. I mentioned the broadband or multiband efficiency. Let's see how we have done it. So this is one of the early papers we published. It is broadband, dual polarized, compact, full wave rectangle. Okay, so that's published in 2015, and this was a very popular reference in this area. As you can see, the design is pretty compact, and we are very pleased with that design. I mentioned the full wave rectifier. So here are some examples. Okay, the first example then is actually a half wave rectifier. Only one diode is used. Okay, and then the second one then is full wave rectifier. As you can see, half wave rectifier actually use the half of the input signal's energy, but a full wave rectifier, then we manage it to get everything, so 100%. So therefore, full wave rectifier obviously is required, because we want it to be broadband. So therefore, we introduced this new design. It's called Granache rectifier. So it's basically two branch to do it, and then we can broaden that the bandwidth. As you can see, the values, for example, for this C2 and the C4, they are different. So therefore, that's the kind of way to do it. And in terms of the bandwidth, we would like to cover the mobile band in the UK and also Wi-Fi. Okay, so as you can see, this is a plot of measured results and simulated results. Okay, energy conversion efficiency as a function of frequency. Okay, so there are 3 peaks corresponding to 3 frequencies of interest to us. And then the figure here, then it's our rectangle in action. So as you can see, in our lab, actually, we can get a kind of a voltage around 0.3 volts. Okay, that basically equivalent to 6 microwatts. Okay, and then at a pretty low ambient power level, minus 35 dBm. So that is a real world example case. I mentioned the nonlinear effects before, and then it's here we show the energy conversion efficiency. So that is a very important parameter. And there are 2 types of curve, the broken lines or solid lines, so they link it to simulation and the measurement results at 3 different frequencies, 1.85, 2.15, and 2.45. You remember these frequencies are the first 2 for mobile and the 2.45 for Wi-Fi. Okay, so as you can see, the peak actually is pretty good. It's nearly 60–70% of energy conversion efficiency, but the conversion efficiency is a function of the input power level. So that is a kind of a drawback. Actually, it's inherited drawback of this rectangular approach. And here is another plot to show how the energy conversion efficiency as a function of the load resistance. As you can see, typically we need the load resistance, not 50 ohm, okay, but actually several K ohms, more than 5 K ohms in order to get the maximum conversion efficiency. So that's a kind of nonlinear effects. We don't like it, okay, but anyway, to deal with it, yes. And then here, it's example. Let's say design 2. We basically divide the band of interest into 3. Okay, so 6 bands, and then we use 3 basically rectifier. Okay, so 1 antenna, but 3 different bands to cover the wide frequency band from 0.55 to 2.45 gigahertz. Okay, so we call this approach called divide and conquer. Okay, and then of course here we added impedance matching network. Okay, so the antenna itself, we use ultra wide, circularly polarized, and kind of log periodic structure. Okay, and as you can see, the currents, okay, at lower frequencies or high frequency mode, and then the hot spots are different. Okay, so in terms of the energy conversion efficiency as a function of frequency, and then as we said, we have 6 bands of interest. So here's 1, 2, 3, 4, 5, and 6. So and so basically they are at the desired frequency bands. Okay, and in terms of the nonlinear effects, and as you can see from this figure against the load resistance, and then actually still not a flat, but it's as long as the resistance are relatively high, it's relatively flat. So that's a kind of a good result. And this is a plot, okay, for indoor and outdoor environment. Okay, as you can see, yeah, we have quite a few peaks corresponding to different services. Yeah, indoor Wi-Fi is here, but outdoor Wi-Fi is gone. Okay, and in terms of the power harvested, as you can see, it's in the kind of microwatts region. Okay, so that's okay for some applications. So to further improve this nonlinear effects performance, yeah, we have tried other designs. Here is another one. Okay, so this one we call it hybrid resistance compression. Okay, so this is a little bit like the complex conjugate approach. Yeah, and the imaginary part of the impedance, yeah, because one is plus, the other is minus, then therefore, yeah, the power is well matched. Okay, so that's the kind of basic idea, and then the work also published a few years ago. Okay, in terms of the results, as you can see, yeah, energy conversion efficiency typically more than 50%, can be 60 or 70%. So, and then another thing we considered was the complexity. Yeah, and as we mentioned, if we match the system to 50 ohm, and then you that's the conventional way. Yeah, antenna by default should be matched to a 50 ohm transmission line or connector, bandpass filter, matching network. We all use 50 ohm as the kind of desired impedance. But the rectifier, okay, the impedance actually is not 50 ohm. Yeah, so it's X plus JY, let's say. If our antenna's input impedance can be X minus JY, then these two, can be connected as a kind of complex conjugate. Yeah, the maximum power transfer from the antenna to the rectifier can be the maximum. So that's the basic idea. Okay, so by doing so, we can eliminate the matching network, make the whole structure very simple. Okay, now the question is how to get your antenna's input impedance not 50 ohm, not 73 ohm, but X minus JY ohm. And then our approach is to make the feeding asymmetrical. Yeah, so here is the result of asymmetrical feeding impedance. Yeah, and then we can basically tune the antenna's impedance. And then here are some designs, symmetrical ones. Yeah, it's in the middle here, 50 ohm. Asymmetrical ones, then it's here. So, and then as a result, and as you can see, the impedance as a function of frequency actually indeed can be tuned. Yeah, and when making it as a rectangle, as you can see how simple this structure is. Yeah, and sorry, the soldering technique is not that good. Yeah, but the whole thing works well. Okay, and then here is the energy conversion efficiency as a function of received power level. As you can see at the peak energy conversion efficiency, even you use different diodes, and then we can get pretty good energy conversion efficiency, 60, 70%. Okay, so that's good. This work also published in IEEE Transactions, and as you can see, broadband high efficiency performance is achieved. Okay, so it's good. And then any practical applications? Yes. And then a local company called Antenna, and then they use this one to power the environmental monitoring sensor. Okay, so actually that is a combination of a solar panel and this kind of rectangle, because the sensor could be used both indoor and outdoor. Okay, and so far so good, but we have one big problem, which is the received power. You remember, pretty small, yeah, microwatts. Only some very small device can be used. So how to increase the total received power? So that is an issue, yeah. The simplest way is, of course, to form array, yeah, to make your rectangle a large one. So therefore, yeah, the total received power can be increased. So how to combine, the received power? Actually, it's not very straightforward. Yeah. So here are some combination methods. For example, what you see here is we call DC combiner. Okay. So you have a rectangle from each element, and then the output from these rectangles, and then combined in DC, either in series or in parallel. Okay, so this is good, yeah. But is this the best? Actually, not necessary, yeah. And then even it's in series or in parallels or hybrid, with both series and parallel. That's an issue. Another possible combination is actually we have RF, yeah, combiner first, yeah, you get the power level higher, and then through just one, yeah, rectangle. You remember, yeah, the rectifier actually can work better if the power level is higher, yeah, than normal ambient power level is pretty small, minus 30 minus 40 dBm. And then at a very low power level, rectifier doesn't work efficiently. Yeah, so this is another one. And of course, we can have hybrid one, yeah, and have both, DC and RF combiner. So which one is the best? Actually, really depend on the scenario. Yeah, there are a few parameters. Okay, so I'm not going to go into the details. Here is a paper, okay, and published last year, and then actually I think they've done an interesting work. Yeah, reviewed various ways to combine them. Okay, so that is wireless energy harvesting at high frequencies. What about low frequency, 50 hertz, 60 hertz? Do we have such a need? Yes. For example, this is power lines. Yeah, and nowadays power lines are called smart grid. Yeah, they monitor a lot of things, but all these monitors are powered by at the moment by battery. And by power lines, certainly they carry a lot of power, a lot of energy. Yeah, so they would like to say, okay, so can we power these devices using the power carried by power lines? Of course, the answer is yes. The question is how to do it. Yeah, and the power lines, the power level is extremely high. It's in kVs, yeah, 1,000 watts, 100,000 watts. Okay, so the basic idea is to use what? Faraday's law. Okay, so if we have a time varying magnetic field, okay, let's say magnetic flux density BEX, okay, passing through a coil, then voltages, yeah, can be generated or induced voltages, yeah, and that is linked to a number of things. For example, how many turns, yeah, how big is the magnetic flux density, and also, yeah, what is the mu, the permeability, effective permeability. A is the cross-section area. So to get the maximum, yeah, induced voltage, then we would like to have the number of turns N to be as large as possible, A cross-section area as large as possible, and also, yeah, mu as large as possible. In many cases, actually, the cross-section, the coil size actually cannot be too big. Here is yeah, example people develop, as you can see, this is far too big for most yeah, monitors. So that's not very good. So therefore we worked on this. The first thing we did, actually, instead of kind of yeah, uniformed ferrite core, we developed this, yeah, we call bow tie core, yeah, a new ferrite antenna. This can also be called, yeah. And then for the beauty of this one is what? It's actually the cross section A. This is, yeah, area A, pretty large, and you can have a lot of coils, yeah, and a lot of ends as well. So as a result, the total induced voltage or power can be very high. So that is a pretty simple but effective design, okay, and also published a few years ago. And a more recent invention is, in addition, well, the ferrite core itself has become this coil, okay, and the green kind of coil here, actually it's ferrite, okay. The brown thing, actually this is the conducting coil, okay. So here is how it's fabricated, made. And then if you compare the conventional coil type, yeah, and use the solenoid, okay, so that is the first big one. And if we use that as reference, our bow tie one then has got 15 times better, okay, in terms of the power level for the same outside magnetic flux density, okay. And then helical one then can see actually increase another 5 times. So as you can see, yeah, and the change we've made is looked relatively small, but the impact is huge. Yeah, so that is a very nice piece of work. We are very pleased with that. And then the idea actually is also now pursued by some companies, okay, to convert it to product. We do have other ways to harvest energy around us. For example, the capacitive coupling approach. Yeah, so basically it's to produce, to use the capacitor, yeah, kind of concept. Even you have, yeah, 2 parallel plate round a kind of domestic, yeah, wire, and then you can actually get energy from the wire as well. And then in terms of the how much power that can be collected, and is summarized in this paper. Actually, as you can see, it is pretty good. It's 100 microwatts, okay, better than our wireless high frequency one, okay. Right, so that is about energy harvesting, okay, from high frequencies to low frequencies. What about wireless power transfer? Wireless power transfer actually is, we can also divide frequencies into low frequency region and the high frequency region. Okay, low frequency basically means the fields are non-radiative, okay, near field. And the high frequency, then the field is radiative, so it's, yeah, far field. And the low frequency side, we can divide well, the device into, say, capacitive coupling or inductive coupling can be further divided into, yeah, resonant or non-resonant approaches, okay. And so for wireless power transfer, we have a new challenge, which is, you know, the power typically much higher. If power is higher, is, you know, your rectangle will work, yeah, can handle the high power. That's actually an issue, yeah. At the moment, we have seen some real world applications, yeah. For example, yeah, just use low frequency coils, yeah. We can wireless charging our mobile phone, yeah, or other devices. Actually, for EV, electrical vehicles, yeah, there are, yeah, prototypes. EV can be charged, yeah, using this basic idea to coils. Yeah, and of course the drawback here is the coils need to be aligned well to get a maximum power transfer. But in practice, these alignments could be an issue. Yeah, so how to achieve high efficiency, better flexibility is a topic we have investigated. Yeah, here is an example about the wireless power transfer using the coils concept. Yeah, two coils, of course. Then it has got mutual coupling inductance. That's the blue line, and then the maximum energy power transfer efficiency. Then it's the red curve. As you can see, there is a kind of optimal separation. But generally speaking, the further away, then the mutual coupling inductance is decreasing, and then the efficiency is decreased. So is it possible, say, we have a relatively flexible range, not so sensitive, to just one distance you get a peak. If you can get a kind of range, that would be great. Okay, so yes, the mutual inductance between two coils, it's like that as a function of the transmitter height. Okay, and if you have two, and then you have another mutual coupling, inductance. Okay, right. What about the difference between M1 and M2? Actually, the difference between them actually is a kind of a constant. So that's good to know. Right, if we use this feature by changing the current, directions, one is clockwise, the other is anti-clockwise. So therefore, if we make the coils, in this way, so therefore we can get a relatively constant mutual inductance. So that's the idea. Here is the design, proposed the structure. And then as you can see now, the wireless power transfer efficiency can be very high, almost 100% over actually quite a decent height. Not just single one, but actually over a range from say 1 centimeters to say 6 centimeters. So that's very good. Here's the demonstration. Okay, as you can see, conventional one, proposed one, and then as you can see, the proposed one is much more robust. It doesn't really matter if it's well aligned or not. The power transfer is strong. Okay, so that's good. And for wireless power transfer, actually, the technology is becoming advanced. So we have some standards developed here. Are just some standards, key standards. I think some of you may have heard of that. And also even for electrical vehicles, and then there is a standard already produced. So that is wireless power transfer at low frequencies. What about high frequencies? High frequencies, then yes, we do have such a need, but this kind of application is not for everybody. And here is an illustration about solar powered satellite. And then if we, for most areas, only daytime we get sunshine, but evenings then no. Satellite then can get sunshine 24 hours a day. So if no sunshine, what about the power coming from your satellite? So that's the kind of idea, right? And then you need to use the satellite to do the relay, transmit the power to either your drone. As we know, if your drone need to fly a long distance at the moment, it's really hard, or you have to cover areas, say, no power or due to a disaster, for example, the power is off. So that's kind of special applications people would like to achieve. So here is a paper, okay, about, demonstrator to transmit wireless power, okay, to Earth, okay, first time. So yes, people are working on that. And of course, for high frequency wireless power transfer, and then normally, the beam could be an issue if not directed to the receiver, then the power conversion efficiency is not very good. So therefore, we need to have a kind of feedback loop to make the beam tracked. Yeah. So this is one of the approach we produce. Here is another one at a millimeter wave. So you can have the liquid wave antenna to eliminate on a number of nodes or device to charging these powers. Okay. And then this work actually received a prize from European Conference on Antenna Propagation. There are other interesting approaches, and then here is another one. Okay, it's a broadband high gain multi-beam energy harvesting device. Yeah, this is a kind of Lomberg type of high gain antenna. And also there are discussions about, simultaneous wireless information and the power transfer system that probably viewed as a 6G kind of direction. Okay, in addition to transmit power, we also transmit information, communication, and at the moment these two are separated, and hopefully in the future can be combined. So that's the kind of vision. So as a kind of a global, big picture, energy start from the sun, going to the satellite and then down to Earth. Then we can use the energy from the sun to power various devices, large or small. And there are some new kind of developments. For example, using new materials, metamaterials, to improve rectangular performance. Some of you may wonder how, and then here is an example. Metamaterials basically can provide pretty wide, radiation pattern, also can be polarization independent or insensitive. So that is good for, especially for wireless energy harvesting point of view. And so this is a paper actually produced by us. A compact dual band wide angle polarization angle independent rectifying. So that can be used for wireless energy harvesting and the power transfer. And we can produce, highly integrated design. As you can see here, antenna rectify highly integrated. This is actually very similar to, you may remember the solar panel we kind of developed in the 2009. And then for low frequency coil coupling, inductive coupling approach, we can also use metamaterials. As you can see here, that we use metamaterial, the original magnetic field flux density goes like that way. Once introduce this metamaterials or metasurface material with and this permeability, okay, mu equals to 0, and then we modify the magnetic flux line and then focus on this receiving coil. Okay, so that is a very interesting approach. We can improve the energy conversion efficiency. Right, almost finished. So talking about our applications, so there are many. As I illustrated here, is just general view. In practice, for consumer electronics, we already enjoy this wireless power transmission to power our toothbrush, mobile phone, watch, or even robot. And also, if you like cooking, and now the new cook actually is an induction approach. For medical application, at the moment, people would like to do it, but I think a very limited product actually on the market. Yeah, and here is a kind of illustration of various possibilities. I think the most attractive one actually is the pacemaker. Yeah, at the moment, battery powered. Every 5-6 years, people have to have an operation to replace the battery. Okay, and for automotive industry and actually wireless power scooters, I think it's already in some countries. For electric vehicle, it's in the lab. I don't think in product yet. Wireless power, the drone, actually, it's something people would like to, realize in practice. And then for space application, I already discussed this. Yeah, a number of countries, including China, is doing it. US, Japan, even UK. Okay. For IoT and other applications, I think this is a popular area for wireless energy harvesting and wireless power transfer. Okay, and generally speaking, wireless energy harvesting and power transfer can be applied to the full range of applications industries. Okay, so because we don't like to replace battery. Here is a plot actually from this website. I think it's very good summary about the frequency. Horizontal, you see the frequency. Vertical is about the application from EV, UUV, consumer electronics, up to aerospace. And in terms of the technology, magnetic coupling, the coils, electric coupling, and wireless microwave power transfer, so on and so forth. Okay, so you remember I said we had a dream to harvest solar energy at a much high efficiencies. So that's not quite realized yet. Our work is still in microwave, but for high frequencies. And then as you can see, some people from industry is doing it as well. Okay, so to conclude, basically rectangle is the key for wireless energy harvesting and the power transfer. We need the knowledge from both the circuit and the field, to make it work well. And we need more ideas and more solutions. Okay, so there is a new IEEE journal dedicated to this area. And also next year, 2026, we at Liverpool harvest international workshop on antenna technology. The paper submission deadline is end of this month, or say the 1st of November. Okay, that's all. Thank you very much. Okay, I think 1 hour, for me.
Thank you, Professor Yi Huang, for this interesting talk. Are there any questions from the audience?
If any questions, you need to shout because I cannot see the chat at the moment.
Sí, están las dos. Okay. Thank you, Professor Yi Huang. It's Yasuhiro Matsumoto from Electrical Engineering Department.
Okay.
A very nice talk about harvesting energy. So I have one question. So you have mentioned about antenna, efficient antenna from 50 to 70% of efficiency, but you have been talking about in a frequency of 1 to 2 gigahertz. So it is possible to increase this frequency. So for a light is a terahertz, tens of a terahertz. So
that's good question. That's a good question.
Okay.
Yes. Short answer is yes. It's possible, but can be realized now. That's a question. As I mentioned, Tesla failed his experiment because his rectified didn't work. Okay. We also failed to achieve our far infrared rectangle. That's also because antenna, I believe it worked. it's really the rectify the diodes. I think at the moment, yeah, into high frequencies, into terahertz, high terahertz, and the efficient diode is an issue. Yeah, to have a rectify, we need diodes to rectify the current or voltage. Yeah, to convert high frequency energy to DC to low one. Yeah, but that's the issue. High frequency, that means the device is tiny and also need to be efficient. At the moment, that's the challenge. I think people working in terahertz, they realize actually, yes, they would like to get it to work, would like to harvest the energy at terahertz or far infrared. Yeah, eventually goes to the optical.
Okay.
Yeah.
Another question. You have mentioned recently they have transmitting energy from the space to the Earth.
Yeah.
So that they are transmitting in a microwave range is a direct beam. And I'm wondering, so if the density of this beam is so high, what is happening with the airplanes that can be in that beam or some objective? So what is the possibility that this,
Yeah, that the beam has to be very narrow. You are absolutely right. Yeah, because the solar, from the satellite, it's pretty high. So the beam has to be narrow. Beam to be narrow, that means the antenna has to be huge.
Mhm.
Yeah, if the beam too wide, then the power transmit to cover too large area. Then the power density got on the Earth, it's too small. Power density too small, then you cannot harvest much energy.
However, if in that beam, some objective can go through this beam, so what happened with this objective?
For example, if the object is a bird, yeah, if the bird will be burned,
Yes.
that's a kind of natural question. Yeah, but the answer people did the calculation. Yeah, from satellite to Earth. Once get to Earth, if people are eliminated or birds, are eliminated, actually power density is pretty small.
Yeah.
Okay, so it should be in the safe level. Yes, but that is a concern we all have. Yes.
Okay, thank you.
Yeah.
Thank you. Any more questions from the audience? Well, Professor Yi Huang, thank you very much for your talk. Very interesting. Thanks for
Thank you.
staying with us today. This,
Okay, my pleasure.
yes,
Okay,
give an applause to the professor.
Okay. Okay, so thank you, everybody. Yeah. Enjoy your conference. Oh, a lot of people in the room. Yeah, thank you.
Yes, thank you.
Okay. Bye-bye.